There should be 6 people here. There are 2.
I wanted to come.
The others thought I was joking. Bobby Sponge said, and I am quoting, Patar, maths. Kelpie actually laughed. Squivin sent a thumbs down emoji without looking up from his pipette. Crabzilla said he had a prior commitment. He was eating chips in the common room. I saw him. They will be fine. We can start. 40% of published preclinical results do not replicate. A substantial fraction of those failures trace directly to statistical decisions made without looking at the data first. This episode is about what you should have looked at. Your data is a shape. Every statistical test you have ever run was a question about that shape. Most researchers never look at it. I am Patar. I flooded the cell culture room twice last month. That has no bearing on whether I understand probability. Those are unrelated skill sets. A distribution is the shape your data makes when you line every measurement up. Every cell count, every absorbance, every survival time you ever recorded. Each one is a person standing at a position on a number line. The distribution is a photograph of where everybody ended up. That is the entire definition. The empirical distribution is not a model. It is not an assumption. It is the data displayed as a shape. When you replace it with a mean and a standard deviation, you are replacing the photograph with a 2-word description. The description is not the photograph. A histogram makes the shape visible. A density plot smooths the edges into a curve. Both are showing you the same thing, where the data actually is. This is where every statistics course should start. It almost never does. A histogram's shape depends on bin width. Too few bins and the structure disappears. Everything looks flat. Too many bins and you are looking at noise. Before you draw any conclusion about shape, plot the data at 2 or 3 different bin widths.
How do you know which one is right?
When the conclusion stops changing.
That's it?
That is it. If moving from 10 bins to 20 bins changes what you think the data looks like, you have not yet found a stable description. Keep going until the shape settles.
I've been making histograms for 15 years, and nobody told me this.
Most people don't know it. Francis Anscombe thought carefully about this in 1973 and constructed 4 datasets to make the point formally: same mean, same standard deviation, same correlation coefficient, to 3 decimal places in all 4.
The same summary statistics for all 4?
Identical. One dataset is a perfect straight line. One has a curved relationship that no linear model will detect. One has a single point doing all the work. Remove it, and the correlation drops to 0. One is a vertical cluster with one extreme horizontal point. 4 completely different datasets. You cannot tell them apart without plotting them.
So the summary statistics are just lying?
They are not lying. They are answering a different question than the one you think you are asking. The mean describes the balance point. It does not describe the shape. You asked about the balance point and then assumed you knew the shape. That is the error. This is Anscombe's Quartet. It has been in every statistics textbook for 50 years. The rate at which biology papers report only means has not reflected this. Look at the data before you summarize it. Always. Before anything else. That is the lesson. Everything after this is the explanation for why. The mean is where the distribution balances. If you printed your histogram on cardboard and balanced it on a pencil, the mean is where the pencil goes, not the middle value, the balance point. For a symmetric shape, those are the same. For a skewed shape, the mean is pulled toward the tail. The pencil is off-center. Variance is the average squared distance of every data point from that balance point. Formally, E, x minus mu squared. Standard deviation is the square root of variance.
Why squared? Why not just take the average distance from the mean?
You can. It is called the mean absolute deviation, and it is a valid measure of spread. Squared distances have better mathematical properties. They are differentiable, which means they work cleanly with optimization and probability theory. The normal distribution is defined in terms of squared deviations. Most of what comes after this depends on squaring.
And the square root just brings it back to normal units?
Variance is in squared units. Nothing actually exists in squared units. The square root puts the spread back into the same units as the data so you can compare them directly. Standard deviation and standard error of the mean are not the same quantity at different scales. They are different quantities describing different things. SD describes your data. SEM describes your uncertainty about one number you calculated from your data, the mean. SEM equals SD divided by the square root of n. Every data point you add shrinks the SM. Your data does not become less variable when you add measurements. Your estimate of the mean becomes more precise. The shape of your data is unchanged.
When would you actually want to report SM?
When your claim is specifically about precision of a mean estimate, a clinical trial reporting the mean effect of a drug wants SEM. The reader needs to know how precisely you measured that effect. A paper showing cell viability across conditions is not making a claim about mean precision. It is making a claim about where the data actually falls. Report SD.
So the problem is people report SM when they mean SD.
The problem is that SM is always smaller than SD, and smaller error bars look more convincing. Before you report SM, ask, would a reader draw different conclusions if they saw the SD instead? The answer is almost always yes. The median is the middle value. Half the data sits below it, half above. It is not pulled by outliers. The IQR, the interquartile range, is the range of the middle 50%. An outlier can be 1 million. The IQR does not care. For skewed data, the median and IQR describe a typical value far more accurately than the mean and SD. A box plot shows the median, the IQR, the range, and individual outliers simultaneously. It contains more information than a bar chart at every sample size.
Is there ever a situation where a bar chart is the right choice?
Yes. When you have one number and no distribution, a single fixed measurement of a constant quantity, the moment you have variability to show, the bar chart is the wrong tool. It hides the shape behind a rectangle. One specific shape appears so often in mathematical theory that the entire field built a second curriculum around it. Symmetric, bell-shaped, mean equals median. The probability of observing a value decreases as you move away from the center in a specific, predictable way. It is called the normal distribution.
If most biology data isn't normal, why does it matter so much?
2 reasons. First, the central limit theorem. Sample means behave approximately normally as n gets large, regardless of the shape of the underlying data. This is why t-tests work even when the raw data is not normal. The test is not testing the raw data, it is testing a mean, and means follow the CLT. Second, the normal distribution has clean mathematical properties that make it tractable to work with analytically. The rest of classical statistics was built on top of it.
What happens when n is small?
The CLT needs room to operate. At n equals 3, you are not in the CLT regime. You are in the regime where you have 3 numbers and you are hoping for the best. The more non-normal the underlying data, the larger n needs to be before the rescue works. There is no clean threshold. It depends on how badly shaped the data is.
So n equals 3 is basically useless statistically?
It is not useless. It is limited. You can still report what you observed. You cannot make strong distributional claims from it. Any summary statistic at n equals 3 should be presented alongside the raw data as individual points in the figure. Show all 3 dots. Let the reader see them. Some distributions have 2 peaks. Bimodal. It means 2 different processes are operating in the same dataset simultaneously.
How do you know it's actually bimodal and not just noise?
You look at the biology first. If your samples came from 2 different sources, 2 cell lines, 2 donor populations, 2 time points, the bimodality is telling you something real. If the samples should be homogeneous and you see 2 peaks, you have a contamination or classification problem. The statistics flags it. The biology explains it. The mean of a bimodal distribution sits in the valley between the peaks. It describes neither group. This is not a rounding error. It is a biological question you have not asked yet. Most biology data is not normal. Cell viability is bounded between 0 and 100. No normal distribution has bounds. It extends theoretically to negative infinity and positive infinity. Every parametric test that assumes normality is structurally wrong for bounded data. This is not an edge case. This is the majority of cell biology data. ELISA absorbance is right skewed. qPCR delta CT values are log normally distributed. Survival times pile up near 0 and have a long tail. These shapes are not accidents. They follow directly from the biology. Right skewed means the tail points right. Most values are small. A few are very large. The mean follows those large values. The median does not. Report the mean of right skewed data as a typical value, and you are describing the average tree in a forest where most trees are small and 3 are enormous. Right skewed data often comes from multiplicative processes. Cell growth is multiplicative. Antibody titers are multiplicative. A log transformation converts multiplication into addition and right skewed distributions into approximately normal ones.
Doesn't transforming the data change the answer?
It changes which question you are answering. Linear scale asks about absolute differences. Log scale asks about fold change. The biology almost always cares about fold change. A two-fold increase in expression is meaningful regardless of whether the baseline is 10 or 10,000. Log scale is not distorting the data. It is describing the scale on which the biology actually operates. Non-parametric alternatives, Mann, Whitney, Yu for 2 groups, Kruskal, Wallace for more, make no distributional assumptions. They are appropriate when the shape is clearly non-normal, or when n is too small to assess normality reliably. The choice of test should follow from the shape of the data, not from what the previous lab member used. Before running any parametric test, make a QQ plot. It asks, where would each point sit if the data were normally distributed? Then it shows where each point actually sits. A straight diagonal line means approximately normal.
What does it look like when the data isn't normal?
It curves. Both ends bending away from the line means heavier tails than normal, more extreme values than you would expect. One end curving in one direction means skew. You know immediately. The entire assessment takes 15 seconds. It is not routinely done because nobody explained it once.
I want to go back and run this on everything I've published.
That is a reasonable impulse. Every statistical test assumes your data has a specific shape. The test will produce a number regardless of whether that assumption holds. The number can be wrong, not because the formula broke, but because the formula answered a question about a version of your data that does not exist. Looking at the shape before you run the test takes under a minute and tells you whether the assumption is reasonable. Most people skip this step because they were never told to do it.
They know now.
New episode every Saturday. That is how long Kelpie, Bobby Sponge, Squiven, and Crabzilla have.